think I did. Let's move on to the second example and then one at the bottom to finish up. So determine the similarity transformation that maps triangle RST to PYZ. Bless you. So they're saying it's going to be a similar figure. And so you can include dilations. And if we look at the grid over here, yeah, we're going to need to include dilation. It says start with RST, so start with the small one. I like to do a dilation first. There's some times where you might not be able to do a pure dilation first, but usually I do that. I want to get the triangles to be the same size. Any ideas what we should dilate by? I'm going to say dilate by a scale factor of 2. How'd you know? What? But why 2? Why not 1.5 or 4? Yeah. So basically, look at the side lengths here. Like this one is a length of 2, this one is a length of 4. So the scale factor there to there is 2. Multiplied by 2. Now be careful. If it had said big triangle to small triangle, you would have said 1/2. Yeah, half is big. Now here's another thing. Say that the triangles had no horizontal or vertical segments, so you couldn't just count. You might say you have to do Pythagorean theorem. No, you don't do Pythagorean theorem the whole thing. Just compare 2 of the sides that match up and count the like this would be like 1 and 2 for slope. This might be like 2 and 4 for slope. And so then you say it's double. Okay, so you don't have to do a full like Pythagorean. You could do Pythagorean theorem. They won't always be horizontal and vertical there. Okay, so that's it. You could have also said 2x, 2y. That's the same as dilate by 2. Now, I need to get what the new shape looks like. Bless you. So I'm going to take each of these points and dilate around the origin by 2. So that one's 1, 1. So if I multiply by 2, it's going to be 2, 2. That one right there is what? 3, 1. So if I multiply by 2, it would be 6, 2. Yes, it goes off the grid. S, 1, 3. Multiply by 2 would be 2, 6. Okay, so what I accomplished there is that I got them to be the same size. Now, if you you also could have done these actually in either order. I just have to give them the same size. Okay, they're now the same size. What do you think? Here to here? Sure. Rotate and really clockwise or counterclockwise doesn't matter for 180. I guess I should. If you don't say around the origin, it's kind of assumed. What else? We learned yesterday that's also equivalent to, you could have said reflect over the x-axis and then over the y-axis. Okay. If you'd like to verify it, we could, I mean, for example, it might be good to verify 1 point. So like, this was 6, 2. Rotating 180, well, it is negative x, negative y. And so this would be negative 6, negative 2, which that one is. Same with 2, 2 would be negative 2, negative 2. And 2, 6 would be negative 2, negative 6. So they'll check out. Okay. That's the similarity transformation. Definitely important. They'll ask you something, here's some figures, what's the scale factor, what's the sequence of transformations. Sometimes they say that too. They might not say similarity transformation. What's the sequence of transformations? So just list the order. Okay, let's answer some questions about this. So in a similarity transformation, y and x. So basically our angles congruent. Y and s. Those going to be congruent? Yeah. Or I should say the same or different, but be the same. Just remember, in similar figures, the angles are congruent. The next one, though, PZ and RT, the lengths, PZ and RT, are certainly not. perimeter of the triangles? Same or different? Yeah. Small. I'm doing the original one, not that one. So, yeah, small and the different areas, certainly different. Slopes of the lines ST and ZY, or YZ. Same? Different? Same. Now, I will say on this one, I'm not putting an asterisk here. This is not always true. For example, if we did, let's say it was this one instead, then that slope and this slope would have been different. So in this one, they end up being the same, but it's more of it could be the same or it could be different. It's not always the case. Okay. Similarity transformations, anything I can answer with that? All right, well, let's finish off with one example. This is kind of nice. It kind of combines what I was talking about with transformations here and what I was talking about with these. So SAS, angle, side angle, SSS, showing two triangles are congruent. It kind of combines them. So here's what it's going to say. Verify the SAS postulate using these two triangles. So basically we're going to show these two triangles are congruent. Here's what I know. I know J and P here are congruent. I know PA is congruent to JO, and I know FP and SJ. So right now, we know from our past that is two triangles by SAS, two sides and an included angle. So they'll be congruent by SAS. What we're going to do, though, is we're going to verify that with transformations. Okay, we're going to verify that with transformations. I helped you out on this one. So I could have really not given you any of this. And you could have said, well, we'll do it in a minute. But I kind of gave you the picture so you can see this one more easily to start. So here's what we're going to do. I'm just going to, not foolproof, I'm just verifying. I'm describing why this is going to work. So the first one is just what we start with. I will give a little reason here. This is what we're doing. Just kind of writing a reason for each one. Okay, let's see what they did next. So really the red triangle, JOS, they're left. But the other triangle is now here. I'm identifying what transformation. Well, the triangles, it's not a dilation. What did they do from here to there? They translate, reflect, or rotate. Translate, they slid. So translate, triangle, what is that? FAP. I'll put so A and O. You could say match up or coincide. Coincide is the word for that. Coincide is the word for overlap or match. So basically, we translated the blue triangle so that it matched with point O. It met up right there. So I'm just saying basically it's just saying what transformation. We did a translation. Okay. Next, so again, really the red triangle stays the same. What are we doing with the blue triangle to get it from there around to here? Translate, reflect, rotate? Yeah, rotate. So for this one, we're going to rotate triangle FAP. I'm going to, so that normally it's around the origin. Well, we don't really have an origin right now. It's just triangles. So we rotated it around point A. Right here. We rotated that around point A. This around here. So rotate triangle FAP around A. I'm going to put so JO and PA. Again, coincide. You could say overlap or coincide is the word for overlap or match. And they will match. I should go back to this. They will match because back here wasn't PA and JO congruent. That was given. Okay, so we know that these are a shared side, that they have the same length. Finally, to get here to there, so I'm mapping the blue triangle to the red one. That one to there, reflection. So finally, I'm just going to reflect triangle FAP over line, you could say JO or PA. But I write line. So I'll say reflect triangle FAP over line PA, or you could say line JO. So basically what did I do? I did I showed the triangles were congruent, but I was using transformations. I just described, well, here to here, I translated. And there and there, we rotated. And here to here, we reflected over. And now the triangles would match up perfectly. And we mapped the blue one to the red one and set it. All right, that was fun.